Okay, physics algebra base, second semester. We're going to do chapter 20, sections 4 and 5. This is lecture 3 of chapter 20. And we're doing energy, power, and electric circuits. So let's start with our definition of power. Power equals work over time. And you guys know that pretty well. Which means energy over time, which means we could start with our potential energy. If our potential energy is equal to Q times our voltage, so whatever the little charge is that's getting pushed around, then that means that our power is equal to Q times our voltage divided by T. But Q times our voltage, I'm sorry, Q over T is equal to what? Okay, stop right here and tell me what Q, your charge divided by time is. What is that equal to? Okay, well, that's equal to your current, right? So we can then say that our power is equal to our current times our voltage. And if we use V equals IR, then we can do some cool stuff. And we can show that not only does P equal IV, but P equals I squared R and V squared over R. Okay? So power is easy to calculate. You can do it all kinds of different ways depending on what you're given. However, finding power loss in a specific component of resistance means that we have to be careful. Okay? We've got to be careful. So here's a circuit. This circuit is supplying a voltage to these two resistors, and there's some current that's going through the whole thing, and we want to know maybe what is the power lost on this guy, or we might want to know what it is across this guy or what it is across this guy. So we either have to figure out what the voltage is from VAB, or we need to figure out VBC, but the voltage of the battery isn't going to work for us. Okay, we can't just do this voltage for both R and R2 because that'll give us the wrong answer. Okay, so this gets a little tricky, and we're going to see in chapter 21 we can find our current by finding the equivalent resistance for both R and R1 and R2, just like we did with capacitors. And we're going to find that this is how you do it. So if we add 90 plus 10, we're going to get 100 ohms. So then we can go through and we can figure out what that current is over the whole circuit. That is 0.12 amps. Okay, now this is the current, all right, for sure, flowing through each of the resistors, okay, because they're in what we call series. So the current that's going through R1 has to be the same current going through R2, all right? Okay, well, we'll talk more about that later. But we want to just find the power used in R1. So if we just want to find the power used in R1, then we're going to take our current through R1 and then multiply by R1, all right? So that's 0.12 squared times 10. Well, that ends up giving us this as our power. This is the correct answer. And if we want to do it through power or through 2, then we square our current again and we multiply by 90 ohms, which is going to give us 1.296 watts. So what would have happened had we done the total voltage something else? So here's why. Here's why all this works. But before we go, I want to say that this is the right way to get your power lost. And if you know exactly the amount of current going through that object, the resistor, you can get your power lost, okay, or power used, or however they say it. They'll say what's the power dissipated, for example. Well, that is this power. So you have to figure out what the current is through that very resistor that you're talking about, and then you can do it. So here's why. Let's say our current we know is going through is 1.2 amps. And then you quickly, because you don't want to go through and figure out what the voltage is from A to B, and you go, oh, well, that's my battery's voltage, and then you'll find that you're losing 1.44 watts. But what did we say above? It's 0.144. So you're off by a factor of 10, and it's all because you didn't use the right voltage. So we just really want to find the power for 1. So we need to find what that voltage is. We need to find what this VAB is. Okay, so VAB is 10% of the voltage of the battery. Why? Because R1 is 10% of the total 100 ohms. So we only want to use 10% of it. Well, 10% of the total battery voltage is VAB. That's 0.12. So now we can do this one, right? Now we can use this because we're using the proper voltage, and we can say, oh, well, 0.12 is my current. This is the voltage across my resistor, and now I get the right answer. Okay, that's the right answer. They're the same. There's a third way, and that would be V squared over R. But again, we need to use VAB, because if we use the battery voltage, we don't want that. We don't want the battery voltage. If we did use VAB, we're going to get the right answer again. So if we did the other one, we get 14.4 watts. That's way too big, right? That is just way too much. All right, so don't make the mistake of using V battery when you really should be using the voltage across the thing. So if you can find the I for the component in question, and you know what the resistance is for the component in question, then you can get the proper power used or dissipated in that component. Okay, power lost. Now, I recommend you do that every time, but if you feel like you can get the V across that component, then by all means you can use this one here, or you can use this one here. Either way, right? As long as you know the current and the resistance. But why would you go to the extra trouble of finding out what VAB is? That's just going out of your way for trouble. Okay, so let's look at our early example in the last lecture of the tungsten resistor. When it's cold, it has a resistance of 0.35, and when it's hot, it has the resistance of 4.61. And if we use the supply, right, this battery, we can do that this time. All right, why? Because there's just one resistor. All right, we don't have multiple components. We don't have resistors in series and parallel and all that other stuff. We don't have to figure out. It's just the current going through, and that's going to work for us. So if we only know that we have a 12 volt battery, right? We've got our 12-volt battery right here. If we only know that, then we can just use P equals V battery squared over our tungsten resistance. So, and then our tungsten there's two of them, right? We've got the low R naught, and then that's going to give us our P naught, power in the first place, and then our power finally. Okay, so this resistor, when it's heated up, actually gives off less power. It's a 30-watt light bulb. Okay, that's a pretty nice powered light bulb. All right, so let's figure out our I initial with the lower resistance and our I final. Okay, what are we going to use to do that? Well, we're going to use our V equals IR, and then we're going to twist that V equals IR to solve for I, and that's this equation right here. So we're going to have two. We're going to have our I initially, and then we're going to have our I finally. So since there's no resistance initially, hardly any at all, then our current is a lot. And that's the reason our current is so big that's the reason we lose so many watts initially. So that's the same as that. And that's a lot of watts. So as the resistance goes up, believe it or not, we actually bring down our current, and therefore our wattage, the amount of power used goes down. And that's this one. So it's a good thing that the tungsten heats up quickly, and that reduces our current flow. And reducing our current flow is exactly what we want to do, so that we don't have such a large power loss. Now, if we know what our power loss is and we know our resistance, can you find the current? Okay, so take a second and think about how you would go about finding the current if you just know your power lost and you know the resistance. What are you going to do? Okay, you can stop right now if you want and then come back, and we're going to do this. So our power is equal to I squared R, and then that means that I squared is equal to our power over R, and then we can solve that for our current, and we'll take our R at the cold temperature. So our power is 411. We're going to divide by our resistance. We're going to take the square root, and that gives us the same large amps that we had earlier. All right, so let's get back to energy. So energy is our power. Oh, I have another thing here. Oh, you cheaters. Okay, so let's get back to energy. Energy usage over time. So our energy is equal to the power times the time. If we know that this is our power and we know that we're doing it for 2 weeks, then what is the amount of energy that we're using in joules? Okay, so you can stop and see if you can figure out what that is, or you can just keep playing and we'll learn together. All right. So what do we got to do? We got to figure out what our time in seconds is, right? Because a joule per second is a watt. So we need to figure out our time in seconds. So we're going to go through and figure out 2 weeks times 7 days times 24 hours times 3,600 seconds. And that's going to give us this large amount of time. And we've got our energy is this 4.3 kilowatts. We're going to multiply by that many seconds, and that's going to give us our 5.2 gigajoules. Another way to look at that is 4.3 times 10 to the 3 times 1.21 times 10 to the 6, and that ends up being 5.2 times 10 to the 9. But a giga is 10 to the 9, okay? So that's a billion, all right? And that's just like a billion bits or bytes or whatever it is, billion bytes on your hard drive. You have 1 gigabyte hard drive. Well, that's a billion bytes, okay? So we want to convert. Why do we want to convert to kilowatt hours? Okay, so here's what we're going to do. We're going to convert to kilowatt hours. I'm doing this for your sake because someday you're going to have to pay your electric bills. If you're not already, we probably are, some of you. So your electricity bill at home uses kilowatt hours, which is our power times time, to figure out the unit of energy. Okay, so if we take kilowatt hours, we're talking about energy. All right. So how many kilowatt hours is this? How many? Go ahead. You figure it out. Keep in mind, a joule is a watt per second. All right, so here you are back because you didn't pause. And I'm just kidding you. You probably paused. I hope so. It's actually easier to start out with our energy is equal to this amount of power times 2 weeks. So we've got our 2 weeks. We're going to multiply by 7 days and then 24 hours per day. That leaves us canceling out. Our day gets canceled, our week gets canceled, and we're left with kilowatt hours. All right? So that gives us this amount of kilowatt hours. And your bill will say, on the bill, it'll say, oh, we're charging you 12 cents per kilowatt hour, or we're charging you 10 cents, or now that we've got higher rates, it might be 14 cents per kilowatt hour, whatever it is. So you go in and you say, okay, our cost is 12 cents per kilowatt hour. Our total cost is going to be that times the amount of kilowatt hours that we used, of course. So then the kilowatt hours are going to cancel, and we're going to left with our dollars. And wow, if you only did 2 weeks, your monthly cost is going to be 2 times that. And 2 times 170, that's $340. That's a lot. That's a big, you got to cut back on your energy usage. I don't know why you use so much. Okay, well, maybe that's just us. All right, so let's do this example here. A light bulb, 60 watts, can last 1,000 hours. And if the cost of 1 kilowatt hour is 12 cents, how much will this bulb cost to run for its whole lifetime? This is called the lifetime cost or the lifetime run cost. You're not including the cost of purchasing the light bulb. You're just the lifetime cost of the energy. So we're going to take the amount of energy that we use. We use this much. We're going to multiply it by our 1,000 hours, and that's going to give us our 60 kilowatt hours. Kilowatt. So if you have 1,000 watts, right, that is equal to 1 kilowatt. Okay, so that's where see, we have 60 watts here, but we're multiplying by 1,000 hours. So essentially we're taking 60 and multiplying it by 1,000. That's where this 1,000 comes in. All right, so that's our 60 kilowatt hours. And we're going to then figure out our cost. So our cost is the 12 cents per kilowatt hour. We're going to multiply that by 60 kilowatt hours, and we're going to end up with 720 pennies or $7.20 just for that bulb for its lifetime of energy usage. Okay, well, stay tuned. We've got our final lecture for chapter 20 coming up, and that is lecture 4, 20.6. Okay.